let A and B be two integers with B not equal to 0. A is called divisible by B if there exists another integer q such that A is equal to BQ, written as B divides A, read as B divides A, or A is divisible by B. For example, 2 divides 4 because 4 is equal to 2 dot 2. A is equal to BQ, then B divides A. 2 divides 6 because 6 is equal to 2 dot 3. A is equal to BQ, then B divides A. Similarly, 3 divides 6 if because 6 is equal to 3 dot 2. A is equal to B dot Q, then B divides A. We can see that here if a number is product of if an integer is a product of two integers, then both integers divides the number as 6 is equal to 2 dot 3, 6 is equal to 3 dot 2, 2 divides 6, 3 divides 6. Now we discuss properties. Properties of divisibility. Number 8. A divides 0 for all. A belongs to Z. It means each integer divides 0. Each integer divides 0 because 0 can be written as A dot 0. 0 is equal to A dot 0. It means 0 is a product of two integers. One is A and other is 0. Then first number divides 0. This implies that A divides 0. Now the property number 2 is 1 divides A for all A belongs to Z. Each for each integer Z, for each integer of Z A, 1 divides a. It means 1 divides every integer. 1 divides every integer because a is equal to 1 dot a. Any integer can be written as a product of 1 and itself. Therefore, the first number 1 divides a. The property number is 3 is a divides a. For all a belongs to the each integer each integer divides itself, non-zero integers. For all a not equal to 0, because 0 cannot be divided by 0. Any number cannot be divided by 0 because a can be written as a dot 1. Any integer can be written as the product of itself and 1, and by definition this implies that first number divides this number. Property number 4. If a divides b, then a divides bc, where c is any other integer. Now we prove this. Let a divides b. First we suppose we take a divides b and then we prove a divides bc. This implies that b is equal to aq, where q belongs to z. By definition of divisibility, this is due to by definition of divisibility. Multiplying equation 1 by c. This implies that BC is equal to AQC or QC belongs to Z. If since Q is another integer and C is also an integer, the product of two integer is another integer. Therefore, Q belongs to Z, C belongs to Z. Therefore, QC belongs to Z. So we can write BC is equal to AQ prime, where Q prime is another integer. QC, product of QC belongs to Z. The BC is a product of A and Q prime. Therefore, A divides BC. A divides BC. Property number 5. If A divides B and A divides C, implies that A divides bx plus cy. Bx plus cy is the linear combination of b and c. It means we can say if a number divides, if an integer divides two another integers, then this number divides the linear combination of the integers. If a divides b and a divides c, then a divides bx plus cy, and bx plus cy is the linear combination of b and c. If a number a divides two numbers b and c, then a divides the linear combination of b and c. Now we prove it. Let a divides b and a divides c. Then, by definition of divisibility, this implies that there exist integers q1 and q2 such that from first division a divides b implies b is equal to aq, and a divides c implies c is equal to aq. This one is q1 and this is q2. The quotient may be different. Multiplying equation 1 by x and equation 2 by y, we get bx is equal to a q1x and cy is equal to a q2y. Adding above equations, now we add these equations. Left hand side is added to left and right hand side is added to right. Bx plus cy is equal to aq1x plus aq2y. Taking common a from this expression, we have a is equal to q1x plus q2y. Since q1, q2, x and y are all integers, therefore their combination is also another integer. So we can write a dot q3, where q3 is equal to q1x plus q2y belongs to z. Bx plus cy is equal to product of two integers. The first integer divides this combination. A divides bx plus cy, which is required proof. Thank you.